Okay, so now we are looking at types of collisions. So we are looking at collisions at isolated systems. That means there's no external forces. So if there's no external force, momentum is always conserved. Okay. Now the question is kinetic energy conserved as well? So for instance, when the gas molecules in the room are colliding, kinetic energy is conserved. So in all those atomic level collisions, those are all elastic collisions. Kinetic energy is conserved. But when two cars collide, a lot of the kinetic energy is lost. Now, if you play pool, their kinetic energy is conserved to a good extent. Okay, but again, momentum is always conserved. Okay, so now if the final kinetic energy is less than the initial kinetic energy, the collision is called inelastic collision. Okay, and when you do the collisions lab, you'll see all of this stuff. You'll see an inelastic collision and you'll see an elastic collision. If the final kinetic energy is okay, so well, some people don't define it this way. Now, perfectly inelastic collision is one where if the two objects stick together, if two objects are colliding. Okay, so now this is so this is not how this term is generally defined. So a perfectly inelastic collision is when the two objects stick together, and when you do the collisions lab simulation, you'll see that. Okay, so here's the, if the final kinetic energy is equal to the initial kinetic energy, if the kinetic energy is conserved, then the collision is called an elastic collision. Okay, that's now if the final kinetic energy is greater than the initial kinetic energy, that an explosion happened. So and again, even in an explosion, momentum is conserved. Okay, so we'll look at various collisions. So we'll look at inelastic and elastic collisions. So again, in all collisions, momentum is conserved, and if kinetic energy is conserved, then the collision is elastic. If kinetic energy is not conserved, then it's an inelastic collision. Okay. So here are some simulations that you guys can go look and play. Let's see if I can play this here. No, I can't play it on my iPad. So you'll have to go look at them in your computers, okay, and play with the simulation, okay. So here are two objects headed toward each other and they'll collide. And in this problem, they happen to stick together. So this is a perfectly inelastic collision and they move in that direction. So what we learned is the total momenta of these two particles should equal the momenta of these two particles after the collision. Okay, and that's the law we learned. All right. So this is a perfectly inelastic collision. Okay, so this is a perfectly inelastic collision when they stick together. Okay. And it turns out that from conservation of momentum, we can precisely calculate this velocity, and that's what you'll see in the next slide. Okay, so what we know is, so what we're looking at is a perfectly inelastic collision. The two objects are going to stick together. And we're looking at the collision in one dimension, meaning these objects are moving in a straight line. Okay, so it's not a glancing collision. Okay, so everything is happening in one dimension. That's just to keep things simple here. Okay, so the momenta of the two objects before the collision is this thing. So M1, V1 initials, that's the momenta of this guy before the collision. M2, V2 initial, that's the momenta of this guy before the collision. So this is the initial momentum. And after they collide, again, they've stuck together, so their velocities are the same. And so the total mass is that. So that's the final momentum. And so you can calculate the final velocity. Final velocity is initial momenta divided by the two masses. So if the two objects stick together, they have to be traveling at that velocity. So that's, and see, that's pretty powerful. What this is telling you is no matter what the material of these things are, no matter how they're built, if they stick together, they are going to go at that speed. Somebody had a question? Did somebody have a question? Okay. All right, so this is a perfectly inelastic collision. Now we'll consider elastic collisions. What is an elastic collision? In all collision, momenta is conserved, but in an elastic collision, kinetic energy is conserved as well. Okay, so so when an elastic collision happens, the objects will never stick together, and you guys can go and check out those links, and there are links to simulations that you should try. Okay, so now we're considering an elastic collision in one dimension. Okay, so all objects are going to move in a straight line. So here are two objects coming at each other, and they collide and they bounce off like that. So the momenta before the collision should equal the momenta after the collision, which is this statement. The momenta before the collision for the two objects is equal to the momenta after the collision. And that's what the subscript final is and the subscript initial is. And now, since this is an elastic collision, kinetic energy is also conserved. So the kinetic energy of these two guys, kinetic energy of particle 1, particle 2, and the subscript I telling you initial kinetic energy is equal to final kinetic energy. Okay, so these two conditions must be satisfied in this elastic collision. Okay, so if the velocities are unknown, since you have two equations, you can solve for two quantities. Okay, that's what that means. Now you will be solving problems using these two equations, but it turns out because this is a quadratic equation, it can get a little messy to solve these quadratic equations. But if the collision is in one dimension and it's an elastic collision, these two equations can be simplified to these two equations. And the reason this is nice is because now this is a linear equation. See, this was a quadratic equation, and both of these equations are linear in velocity. And this is much better to handle. Now, what this equation is telling you is, see, this term is relative velocity. What this is telling you is, for instance, so if this were going at 10 meters per second and this guy is coming at 5 meters per second, if you were sitting on him, this guy will appear to come at you at 15 meters per second. That's what this term tells you. 10 minus or minus 5 will be 15 meters per second. And what this tells you is, so if you're sitting on him, he comes at you at 15 meters per second. After the collision, you bounce off. And if you're sitting on him, this guy will appear to move away at 15 meters per second. So if you were sitting on him and looking at the collision, he's coming at you at 15 meters per second. And after the collision, he goes away at 15 meters per second. That's what this equation is telling me. Okay. So now again, this will only work for elastic collisions in one dimension. Okay, so remember that. Okay, so now we'll consider a slightly more complicated situation, a 2D collision. So now objects are allowed to move in 2 dimensions. So this could be you playing pool. Okay, so here's the cue ball and there's the object ball. They collide and they move away like that. Again, momentum before the collision should equal momentum after the collision. But now since we're considering 2 dimensions, you'll have to look at components. So now we're looking at 2 dimensions, P final, and so their X component should match. and their y component should match. Okay, so that's what we'll have to do. Okay, so, and that's what's written here. So the x components initially equal to x component after the collision. The y component of the momenta before the collision is equal to y component of the momenta after the collision. And in addition, if the collision is elastic, then this equation is true as well. Okay, kinetic energy before is equal to kinetic energy after the collision. Okay, and so now you have three equations that need to be satisfied, and you can use these to solve problems. All right. Again, go to this simulation. I can't go to that simulation on my iPad, but go to that. I suggest you go to that simulation and try it out. Okay. All right. Now we're coming to a different topic, so we'll pause and I'll stop this recording.